Okay, hello everyone. This video is to go over lesson 2.5, which is on continuity. So in the box here, it defines what a continuous function is. And the idea is really simple. A continuous function is a function that can be drawn without lifting your pencil from the paper. Okay, so if I was just to do a quick example, grab my pen here. This is a continuous function, okay, because I didn't have to lift my pen. However, some of those piecewise functions we were looking at, that would not be continuous. So a function that is not continuous at a certain point, we say it's discontinuous at that point. So this would be a discontinuous function. And the first example would be a continuous function. A lot of the functions we've seen before are continuous. So polynomials, those bumpy functions, they are all continuous. Root functions, they are continuous. Some rational functions, if they don't have any asymptotes or holes, they are continuous. And trig functions, which we haven't discussed much yet, but the people who've taken pre-calc 12 will know that cos and sin x, they kind of look like waves. They are continuous as well. So down below here, we're going to look at some examples of discontinuities that can occur in certain functions. So the first one here, we see a hole in the graph, and we've seen that a few times before. That's called a removable discontinuity because one point has been removed. So I've already started writing it there. Remove, oops. Okay. The second type of discontinuity that can happen is at an asymptote, and this is called an infinite discontinuity. You see here there's a point defined at the asymptote. That's not always the case. Usually we actually don't have a point there, but there can be. And the last type is with these piecewise functions, you can get a jump discontinuity because the function jumps from one point to another as you draw it. Okay. So those are the only three types of discontinuities. So one thing you'll be asked to do in your assignment is to look at different examples and define what type of discontinuity it is. So those are the three. Next, we're going to look at the actual definition, the more formal mathematical definition of a function being continuous. So in order to be able to draw a function without lifting your pen, you have to have three things that are true at each point. One thing is that the function must, of course, be defined. Second, the limit at that point must exist. And also that value of the limit must equal the value of the function at that point. So we're going to look at some examples where one of those three rules breaks down, and that's why it's discontinuous. So our first example here is the function 1 over x. I'm just going to show you what that function looks like, and then we'll discuss what type of discontinuity there is. So I'm going to go to my Desmos screen, and this function has an asymptote at x equals 0. That's because we're dividing by 0 at x equals 0, and so that's an infinite discontinuity. Okay, and the reason why it's discontinuous there is because the function's not defined there. We can't divide by 0. Function's not defined at 0. So we can say f of x is not continuous at x equals 0 since it is not. I'm not expecting you to know what the graph of 1 over x looks like. However, if I were to give you the graph of 1 over x, I'd expect you to know what type of discontinuity there is. And so I'll just draw the graph here. Again, I won't expect you to know what the graph looks like. But given the graph, you should know what type of discontinuity there is. So since there's an asymptote, the graph goes off to infinity. So it is a infinite continuity. example we have is a piecewise function. I'm going to show you the graph in a minute. And this is a case where the function is defined everywhere. 2x and x squared are both defined for all x values. So in our definition, number 1 is true, f of a is defined. However, at the point x equals 1, we're going to have a look at our decimals graph and see what happens. I'm going to take away the 1 over x function. I'm going to graph the g of x function. Notice that there's a jump there, right? So the limit actually doesn't exist at x equals 1 because the function from the left is approaching 2, but from the right, the function is approaching 1. So the limit does not exist. So from our definition, number 2 is not true at x equals 1. So the limit, I'll write this formula. The limit from x goes to 1 from the left of f of x times 1, which is 2. Yes, that's right. And the limit as x goes to 1 from the right of x equals 1 squared, which is 1. I'm just plugging the x value into each part of the function. So the limit doesn't exist. Remember, if you're going from the left and the right and they're different answers, then the limit does not exist. So therefore, the limit as x goes to 1, this function does not exist. Therefore, it's discontinuous. And we saw from the graph, it is a jump And the last example is a rational function. And again, I'm going to show you the graph, see what's going on here. And this is the case where the limit actually does exist. The function is not defined, though, at x equals -1, but it's not an asymptote discontinuity. So we'll have a look at the graph. People who've taken pre-calc 12 will recognize this situation. So the graph is actually a straight line with a hole in it at x equals -1. So this is a removable discontinuity. This not continuous at x equals -1 because f of -1 is not defined. I'm going to quickly sketch the graph. So here. Oh, there we go. So this is a removable continuity. For those who are curious, I'm not going to expect you to know this when the holes show up and when the asymptotes show up, but if you're curious, when you factor the numerator, it factors to x plus 1, and the denominator is x plus 1. See how we have a cancellation there? So when that cancellation occurs, that's when your holes show up. It's still not defined at x equals -1, but the cancellation creates a hole instead of an asymptote, if you're curious. Okay, so those are 3 examples of the 3 types. Again, you'll have to identify the 3 types given a graph. Okay. Now we're going to look at a little bit more specifically when we're coming in from the left or the right. So you can be discontinuous. However, the function can be continuous from only the right side or from the left side. So, and I'll show you an example in a second. So if you're continuous from the right, then the limit as x approaches a from the right has to equal the function value at a. And if you're continuous from the left only, then as you approach from the left, the limit equals the function value at a. We're going to look at an example to make that clear. So look at example 3 here. We're going to determine at each point if the function is continuous Is it not? Is it discontinuous? And then what type of discontinuity is it? Okay, so let's first look at x equals 0. So at x equals 0, look, I don't have to lift my pen as I go through that point. There's no jump, there's no infinite discontinuity, no asymptote, no hole in the graph. So at x equals 0, we have a continuous function. At x equals 1, we have a hole in the graph. Okay. The function's not defined there, so it's not continuous from the right or left. It is a removable discontinuity. At x equals 3, we see as we approach 3 from the left side, the limit would be, well, it doesn't have a y value here, but the limit would equal the function value from the left. So it is continuous from the left, and then there's a jump discontinuity. So it's a jump discontinuity. And it's continuous from the left. Because the limit is equal to the function value as you're coming in from the left, because we have the colored in circle here. So actually, continuous from the left and right, these are only really applicable for jump discontinuity. So let's write that in there. Okay. And at x equals 5, we have a discontinuity. We have to lift our pen, and we have a hole in the graph, so it is a removable discontinuity. So here's an application of continuity. I'm just going to leave my hands. There we go. It's called the intermediate value theorem, and it says, so I'm going to read the theorem out, and then I'll show an example to make it clear. So suppose f is continuous, so we don't lift our pen, on a closed interval from a to b. From x equals a to x equals b, we're not lifting our pen when we draw this function. And let's say n is some number between f of a and f of b. Okay. And there must exist a number c in ab such that f of c equals n. Okay, so let's just draw that because it makes much more sense when we draw it. Okay. So let's say that we have a function, and I'm going to just label a and b anywhere. They can be any x values, a and b. And we're going to pick any, I'm just going to draw a random graph, but I'll pick one below the x-axis and one above it. Okay, so let's say f of a is here. They don't have to be above and below the x-axis, it's just for this demonstration, it makes it easier. And so when you draw your continuous function, let's say n is 0 in this case. So let's say n is here. There's no way to draw this function without crossing the x-axis. Like, you have to cross it. So if I know that my function value is negative at a and my function value is positive at b, then I know it must cross the x-axis somewhere in between. There's no way to draw it without lifting your pen otherwise. So I have to at least cross it once. It might actually cross more than once, but you have to at least cross it once. So this is actually how calculators find roots. They look for points where you have a negative value on one side and a positive on the other, or vice versa, and then they shorten the window, and that's how they find roots. So we're going to actually do a question here where we find the root. So use the value, well, we don't find the root, but we say that there is one. So use the intermediate value theorem to show that the equation 4x cubed minus 6x squared plus 3x minus 2 has an x-intercept between 1 and 2. So normally we wouldn't know really how to factor that or how to graph that without the help of Desmos. However, we can use this theorem to show that at least there is an x-intercept between 1 and 2. So all we have to do is say that f of x is continuous we don't have to use our pen. And also, we're going to plug in 1, and we're going to plug in 2 and see what they are. So if I plug in 1, you can just believe me, 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2 is negative 1. And if I plug in 2 into the function, I get 12. So that means, because it's continuous, I'm not lifting my pen, I start at a negative value and I work my way to a positive value. I must cross 0 at some point. So there must be a number. So by the intermediate value theorem, you can use IVT for short. There must be a number C, so 1 less than C less than 2, where f of C equals 0. Which is an x-intercept. There, that's it. That's all you have to say. So you just have to plug in the 2 points and show that one's negative, one's positive. You must cross 0 at some point then, because the function is. Okay, so your assignment is listed here. And the required questions, again, the full solutions are on Teams. For sketching graphs, if it asks you to do that, you can use Desmos. On a quiz or a test, I would always provide you with the graph. And then there's extra practice questions there, which again, you can find the solutions on later. Okay, that is it for 2.5.